The following teacher development program is brought to you by the MultiChoice Africa Foundation.
This is not bad.
Aha, my brand new business. This time I'm going to make money. Lebogang's iced tea. Yeah.
What are you doing?
I'm impressing you. I'm calculating the volume of the tumbler. You see, if you want to get volume, you have to multiply length by breadth by height, then you get volume. Cheers to volume.
But no, you don't do that.
What do you mean you don't do that? You told me that.
That was for a cube. For every shape, the volume calculations are different.
Oh, cute.
Shape and volume are very important, and you'd have to think about that if you wanted to choose a bottle for this.
Will you help me?
No, sorry, not today. I have to get home. I've got to get to Tulani. He needs new clothes for tomorrow's festival. I'll see you.
Hey, what's the problem?
I'm supposed to have 2 liters per day, and now I've lost count of how much I've had.
Aren't you taking this diet of yours a bit too far?
No, it's just a short detox. I mean, I need it after that choir festival. Those church mamas just cook for the masses, and it's hard to resist.
Well, the other day you were talking about shapes and the volume, blah, blah, blah. So why don't you figure it out yourself?
Of course. Why didn't I think of that? Let's do an illustration. Okay, let's do bottle 1. We'll say this is bottle 1, bottle 2. The top part is almost a triangle, the middle part is a rectangle, and the bottom is a half circle. But in 3D, you have a cone, a cylinder, and a half sphere. Now, for me to calculate how much water I've had, I need to add the volume of the cone and the cylinder from this bottle and add the volume of the cone from this bottle.
You've started the day with 2 full bottles. Just finish each, then you'll know that you've had 4 liters today.
Don't be silly. I'm going to calculate the volume of the cone.
Don't you know it?
You can't always remember these volume formulas. There it is. The volume of a cone is equal to 1 over 3 pi r squared h. Okay, now we need to measure the height of the cone.
Okay, I'll measure it. Doing this. 13, that's 13 centimeters.
13. Right, now we need the diameter of the bottle, and that will also give us the radius.
The diameter? Oh, you mean around the bottle?
Around the bottle? No, the diameter is across, and the radius is half of that. So that's from the midpoint to the edge of the bottle.
Aha, that's 10. 10 centimeters.
So that's 5 centimeters, which when squared is 25. Okay. So that's 3.14 over 3 by 25 by 13.
Oh, where do you get 3.14?
It's pi. It's 3.14.
So it doesn't change, it remains 3.14.
It's a formula, and that's how it stands.
Okay.
Let's make that calculation. 3.14 divided by 3 times 25 times 13. It's about 340 centimeters cubed or 340 milliliters.
So a tin of cold drink can fit in that cone. So that means you've had 2 cones, which is 340, that's 680 milliliters.
Now for the cylinder. Okay, let's look at the formula. Right, okay. So the volume of a cylinder is equal to pi r squared h. We need the height of the cylinder.
It's 17 centimeters.
Take the radius, which we know already is 5 centimeters. We square that again and multiply by pi and by the height.
3.14 multiplied by 25 multiplied by 17 is equal to 1,334.50. So we can make it 1,335 milliliters. So altogether, you drank 2 cones, which is 680 milliliters. Our cylinder is that's 1,335. 680 plus 1,335 milliliters equals to. So all in all, you've used 2 liters.
Man, you're starting to think in a math literacy way. Pretty soon you'll be teaching volume like a pro. Impressed?
Jessica Sherman is teaching a lesson on volume using containers. She has placed different containers on the desks and gets the learners to describe them using mathematical language.
This, from here to there, this is a cylinder, right? Okay, now what can you say about this section here?
It's like a triangle.
There's something triangular about it, isn't there? But you can see it's not really a triangle. Okay? If we didn't have the cylinder and we held it this way, can you think of something which has that shape?
A cone.
That's it. Okay, we had an ice cream.
Yes.
Okay, it would look like this, wouldn't it? So this has got, this part is a cone shape, isn't it?
Learners are used to seeing a variety of different shaped containers, but it's a challenge imagining what a 3D container will look like spread out in a 2-dimensional net.
Who knows a lovely chocolate that comes in this shape? Toblerone, that's right. Okay, what shape do we call it?
Triangular.
Both of the ends are triangles and the sides are rectangles. So now you can draw this on your pieces of paper as if it were opened out and flat on the table. We call that a net.
Once the learners have drawn the net of the triangular prism, Jessica makes sure that they have got the relationship of different lengths correct.
This is an equilateral triangle, okay? Okay, so this side here will be the same as that side. What about this one? Will this be the same as anything?
The other side the same as this side.
That will also be the same. Okay, so if it's accurate, then that's how it has to look. And this doesn't look accurate to me. This doesn't look the same size as that.
Most of the learners have guessed the shape of the net correctly. Now Jessica asks them to pull apart the containers on their desks into 2-dimensional nets.
No, I didn't know what it was going to be.
It's amazing that it's a parallelogram.
Well, parallelogram's made out of triangles, isn't it? Yes. Okay, so now we understand.
The learners have to understand what part of the net is used to make the shape and which bits are just used for fastening, known as flaps.
Okay, and now what can you say about these things? They're also just flaps, that's right. Okay, so they're not really part of the shape. They're extras, right. Now we've got our hexagon and we've got our 6 rectangles.
Jessica hands out a paper net to the learners. They have to cut out the net and assemble it.
This is our circle, and when we turn it over on its side, this will be our base, and then once we put it down, we'll then have our cylinder.
Next, the learners have to calculate the volume of the container they built. Most learners only know the formula for the volume of a rectangular prism: length times breadth times height. When asked the formula for calculating volume for another container, they almost always use this formula incorrectly.
So how would you work out the volume of this? You can't use length, breadth and height, can you?
Pi r squared.
But we're doing a half cylinder.
The formula for a cylinder is pi r squared times height. So for the formula for a half cylinder, you would divide this by 2. In this group, the learners have forgotten to divide by 2.
Miss Sherman, you've got the answer.
Let's have a look. So earlier, Khunsi was saying he thinks you haven't divided by 2. What do you think?
Yes.
You think that you haven't divided by 2?
Yes.
Okay, so see if you can fix it. Yes. You don't have to do the whole thing again.
Okay, let's fix it. So we just have to divide one of these by 2.
I have to divide this one.
This one.
I think this one is better if you divide the whole.
Why? You can even divide this one by 2, still the same.
Then right now we're dividing by 2 the pi, the circle, and we're not dividing the height because then we'll make it shorter. So that's why we mustn't divide the 8. That's why we must divide.
Yeah, we should
from
divide
the-
it.
It wouldn't matter wherever you divide by 2.
Why?
It's still the same.
Khunsi, you can't divide the height by 2.
You divide it
And we're not cutting
pi
the
r squared.
height.
If this
the
was a
height.
full circle, you wouldn't have to divide by 2, right?
Yes.
So you'll get your answer.
Oh,
But if
yeah.
it was a half circle, you
Because
just
we did
divide
it
it
as
by
a full
2.
circle. We did it as a full
Yes,
circle. We didn't
that's why
divide
you
it by
can
2.
divide anywhere by 2.
Jessica relates capacity to volume by showing the learners a cubed centimeter model and comparing it to a milliliter.
So that's the amount of liquid that would fit inside this. Okay, so that is why they are equivalent to each other.
Now it's time for the learners to get creative. Jessica asked them to design a container for a youth drink. The catch is it must contain 250 milliliters.
The kind of design that we have is we're going to make it a submarine. We have a cylindrical base and then we have a triangular prism on top. 200 milliliters can fit into this cylinder and then the other 50 milliliters can fit into the triangle.
Before the learners can build their containers, they have to do the calculations to check that their shape will have the correct volume. The problem is, most of the volume formulas have so many variables, they don't know where to start. Jessica explains that you should decide on some of the measurements so that you just have one unknown measurement.
Okay, so you need to find the factors now of 250. What times what will give you 250? So we could choose 10 for the length and 5 for the breadth. If we want to work out h, we say that will be 250 divided by 50, that's right. Okay, and that will come to 5. Okay, therefore h equals 5.
These learners have half their measurements by mistake. They come up with a container that is 8 times too small. The group who designed the most accurate container have chosen a rather unusual shape. They've chosen a cylinder with a radius of 6 centimeters, which means that the height is only about 2 centimeters.
Pie juice. Why did you call it pie juice?
The container is shaped as a, you know.
The girl who worked on this is normally very disinterested in her work and takes no pride, etc. So when she came up with this, and in fact out of all of these, this is the one that's accurate. This one works. This one will contain 250 mils. The others all have mistakes in them, and their one worked.
This kind of lesson allows for real creativity among learners and can stimulate a lot of mathematical discussion.
Okay, thank you, everybody.
Which one of these do you prefer?
This one is cool.
Ha!
It's a cube, ne?
Well, it's not completely a square. The ones which look like rectangles are called cuboid.
I can't decide between the cylindrical can and the spherical fruit juice bottle.
No, that's not a perfect sphere, but it will do for now.
I also quite like the shape of this, but in a bigger version, of course.
Now that's interesting. A tetrahedron.
What a nice word, a tetrahedron. It makes me think. What about tetra iced tea?
I think even a professional container designer would think that's cool, but not for tea.
But this is my design. Nobody's supposed to choose this design.
What I do is called packaging development, and it involves designing a pack for a certain product, which might be a new product or a relaunch of an existing product. And yes, it involves a lot of calculations and measuring, because everything has to be right. As we know, different products have got different densities, which is why you cannot take a 500-gram tub and that is designed for margarine and pack cheese in it, because the density, they are not the same. You might find that for cheese, it might look like the product, the tub is almost empty or it's too full. If you look at all the corners, you find that there's a piece of the tub there that's going out. This piece is called a nesting shoulder. What it does is it makes sure that when you stack your tabs, it's not too much vacuum that is created such that you cannot take one tab up. Because when you pack, you want to be able to take one tab each second so that your machine runs at the fastest speed as it can. So everything that you see on packaging, most of the time, it's there for a purpose.
You also use maths literacy when deciding which box to pack your products into.
What makes a box, you have 3 materials. You've got an outer liner, and then you've got an inner liner. And then in between your liners, you've got another material which we call corrugated material. If you look closely to these 2 boxes, you'll see that the white box has got only 1 corrugated material, and the brown box has got 2 corrugated materials. And that has to do with the strength that you need for your box. Because if you have a tub that is not very strong, then it means that you need a stronger box, which is this box. But if you have a tub that is quite strong or a bottle that is quite strong, then you do not need this box, you need this one.
No, Lebogang, take this one. No, Lebogang, this one. No, take this one. No, that one. No, that one. That one.
This is still my favorite shape.